Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to finish discussing cloud storage. You might remember Amazon S3. And before we start, I have a question for you, and then I'll take it from there. So, tell me, which one of these cannot be stored as an object on top of S3? Answer A, is it the first episode of Star Trek Discovery? Answer B, is it the 300 petabyte dataset containing proton collisions released by CERN? Answer C, the static pages of a website. Answer D, an archived backup of my 2 terabyte hard disk. 3 can be stored on S3, and one of them cannot be stored on S3. As a single object, right? I'm giving you a bit of time to wake up. For those of you who see this for the first time, you can go to the URL that you see on the top, eduapp-app1.ethz.ch, and you can log in with your ETH login and password there. Or you can use the app on your smartphone. All right, then let's look at the answers. I think there are many more people on the room and on chat, on Zoom chat as those answering, but nevertheless, we have a majority, and the majority is correct. 300 petabytes cannot be stored on top of S3 because the size of the largest object you can put on S3 is 5 terabytes exactly. That's the largest you can do. So 300 petabytes, that needs to be done differently. The first episode of Star Trek Discovery, no problem, that fits in 5 terabytes. The static pages of a website also fit in 5 terabytes, even if you would have a file with all of them that still fits. To have 2 terabytes for the hard disk is also no problem at all. Okay, so now let me switch back to the slides. Okay, so speaking about data sets. So I told you there's many ways you can use S3, right? You can use it to store pictures, to store videos. If you are a subscribed video on-demand streaming service like Netflix, Disney Plus, and so on, you can also use cloud storage as your backend. If you are an encrypted storage provider, you can also use S3 as the backend. You can host static pages also as a backend. It's one of the cheapest ways of storing, actually, of hosting a static website. And finally, we can put data, which is something that came a bit later, but you can also use a service like this to put your data set, and then we see how you query them. But I just wanted to say one thing that's also popped up in a discussion. So even though the largest objects you can store on S3 are 5 terabytes, in practice, that may not always be a good idea. The problem, if you try to upload from your laptop, let's say you want to upload a data set that is a single 5 terabyte file. What's going to happen is that you're going to start the transfer, but then there is a good chance it's going to fail for various reasons, like for the network or whatever, and then you have to try a few times before it actually works. This is because of the very large file. I'm sure you've all experienced this when you try to download, for example, even an OS update might not work the first time. You might need to try a second time. This is the problem with extremely large files. So there are 2 ways to solve this. One of them is simply, as a user, to split your data set into smaller files, commonly a few 100 megabytes. That's kind of a size that people tend to like. And instead of uploading a single 5 terabyte object, you will upload instead 5,000 objects that are each 1 gigabyte, for example. The reason it works better is that the individual objects, most of them will succeed. And if some of them don't, you just try again, but only with those that don't succeed. And that's actually much easier to handle, right? Because the worst case, there's just a few objects you have to try again, instead of the whole 5 terabytes starting from scratch. So this is the first thing you can do. And in fact, for data sets, people commonly do this. If you look at this screen right here, you will see that these are plenty of objects on S3, and they are each 500 megabytes, right? And it doesn't matter how they are called. It can be incremental integers. This is the reason it's called like that. I think I use the command line that automatically splits the lines over multiple files, and it uses these incremental letters. But what you see here is that we have multiple objects that each have 500 megabytes. We could have uploaded the entire data set that would maybe have been a few 100 gigabytes, I don't know. But again, that would have been tough. It's much easier to upload many smaller objects. And on top of that, typically a client is able to upload several of them in parallel. So you're not just uploading sequentially one at a time, but you can, for example, upload 5 at the same time, right? So this is one of the reasons why a lot of data sets look like this. There is a second possibility, but it is a bit more advanced. If you really, really want to upload a 5 terabyte data set, but you would like to do it in a more reliable way, the S3 API, the REST API, if you look into more details, has a way of not uploading in a single time, but to cut the file into parts. And then you upload part 1, part 2, part 3 to the server. And at the end, once you have uploaded all of the parts, you tell the server, by the way, all of these parts that I have uploaded to you, part 1, 2, 3, and all the way to part 10 in that order, now please make them a single object. The API allows you to do that. At the end, you will have your 5 terabyte object, but the trick when you uploaded it was that you uploaded it into different parts, right? This is a bit more advanced, and I think that not a lot of people actually do this. So the preferred way is really to just cut it into multiple objects that are much smaller. All right, for whom is that clear? All right, who experienced this, like trying to download or upload a huge file and it just didn't work the first time? Right, so this is practical experience. This is really the everyday experience of actually using systems like that. All right, so this is the first trick, practical trick, to cut it into smaller parts. We'll see that they are often called shards, these parts. All right, now a few more concluding remarks on S3. There are many ways people use S3. And there is a standard way that has the kind of the regular price that is always available, highly available. But some people do not care about availability. For example, if this is a backup of your entire company data, you don't need to have it immediately if there is a huge catastrophe that happens. It's okay if you have it like 24 hours later or 48 hours later. In that case, you can ask to pay less. It's cheaper, but what you get in exchange for that is that you may need to wait a little bit until you actually have access to your data. Why? Because it's not going to be directly connected to the internet. It might be stored, for example, on tapes, on tapes that are stored in some warehouse. And then the reason you need 1 or 2 days is that you need these little robots to go get the tapes and then connect them to the network. ETH also has that. If you have data stored on ETH servers, there are backups that are actually stored on tapes. And you really have to imagine this warehouse with little robots that bring the tapes and store the tapes in some place. It's very cheap. The tapes has the cheapest way of storing data you can ever imagine. So you can move the slider between how much you want to pay and how available you would like your data to be. Next, I would like to quickly, it's going to be short, talk about Azure Blob Storage, which is really kind of the same thing as S3, but on a different provider, which is Azure. Why? Because S3 doesn't have really any documentation on how it's implemented. There is no published paper, there are no details, so we don't really know how they actually did it. But Azure did publish. So there is a paper in which they explain how they do it. So it may not be that S3 is implemented in exactly the same way, but it can give you a small idea of how you want to implement cloud storage. So I just want to very quickly, there's not so many slides, very quickly and high level, explain a bit how the blob storage is stored. The first thing I want to say is that on the high level, they're pretty much the same. They are cloud storage services that allow you to store objects. There is a few small differences. For example, in the case of S3, to identify an object, it's a bucket ID plus an object ID, right, on S3. Two things. On Azure, it's three. You identify any object with your account. Think of your email address, for example, and then a container that would be the equivalent of a bucket, and then a blob, binary large object. It's blob. So account, container, and blob. If you consider that a bucket is a bit like a container, the only difference is that in S3, the buckets are worldwide. You cannot have two people naming two buckets the same. But in Azure, within the same account, you need different container names, but worldwide, it's no problem if two customers have the same container name, because the account is also used to identify the object. Then in terms of the API, S3 supports the parts. The part is the way I told you this trick to upload in multiple parts and then at the end paste them all together in a single object. In Azure, you have different ways of exposing the objects. It's called block, append, and page. Don't worry too much about what they actually mean, but it's basically different use cases. So there are the blocks are basically ideal for people that want to store data sets and query the data, as we will in fact see today. Appending is a lot for logging. You know, when you log things, for example, if you have a website keeps a log of everything that happens, everybody who connects to the website at what time and so on. The logs, you always append at the end. You never modify the past data. You just keep appending new things. So there is a kind of storage system that is optimized for appending. And for Azure, there is the last one optimized with pages. The pages are basically to support the virtual machines running on top of their system. But you don't need to understand the details of that. All I'm saying is there are three different flavors of these objects. S3 doesn't distinguish between them. It's just probably it has other ways to optimize. Then in terms of limit, you see that depends whether it's block, append, and page. The limit for the block system in Azure is much higher than 5 terabytes. It's 190. Why? We will see today. I will explain why. Then append is much more limited, but for logs, that's totally fine because you just start a new object when you're done with one. And 8 terabytes for the pages, that would be similar to S3, right? But you see the ballpark is kind of the same. Like think of 100 gigabytes to 100 terabytes, right? As the ballpark. All right, so these are a few of the differences, but apart from that, it basically feels a little bit the same. However, for Azure, we know how it's done inside. So the way it's done is that they have these rooms in the data center that are filled with machines that I already told you about. And so they have every time 10 to 20 racks that themselves have maybe, I don't know, 18 storage nodes, right? You have to imagine that there might be a few computers in there, but many of the nodes that are in there are in fact full of hard drives, right? You might have, I don't know, like 8 hard drives that fit in one of the layers on the rack. In total, a room like that in the data center can store 30 petabytes of data. One room can store 30 petabytes of data. You just multiply very approximately the number of hard drive times the size of one hard drive gives you approximately the storage limits that you can have in there. Now, a room like that, they have thousands of them all over the planet. Maybe there are a few in San Francisco, a few in Washington, a few in Frankfurt, a few in Zurich, a few in Beijing, and so on and so on and so on. It's all over the planet, plenty of rooms like that. So you can imagine that we are well into the exabyte, maybe even zettabyte, maybe, I don't know, zettabyte range today. So a lot of capacity. And what they try to do is they try to not go beyond 80% of the capacity. It means 80% in that case is like 24 petabytes. If you reach 24 petabytes, then what happens is that you start moving the data to another place, maybe from Frankfurt to Berlin, I don't know, as an example. But you try to keep it below 80% because who already experienced a message telling you on your laptop the hard disk is full? Some of you, right? That's exactly the annoying thing that starts happening, and then you start having the system slowing down and so on. That is the reason. So you try to keep it at 80%. And worst case, if it's beyond that, you just move it around to some different data center. Now, this is an illustration on the paper. This is an abstraction of that room right there with all the storage nodes. On the logical level, you can see it as layers. You don't need to know too much about them. But what I want to say here is that within the same room, it's called the storage stamp. Within the same room, you might store the same data twice or 3 times. So it means that in these 30 petabytes, maybe in fact, you can only store 15 if you duplicate everything twice, right? It's just an extra security in case one of the hard drives fails. So there is a so-called replication. What did I say synchronous? Why did I say synchronous here? It's because if you upload a new object, the system will keep you waiting until it stored it twice or 3 times in the same storage step. You have to wait, and it will only confirm after it has stored it multiple times. This is called synchronous. There is another kind of replication across data centers. So for example, you might store a few copies in a room in Frankfurt, and then another copy in Zurich. However, that replication then, it happens on a different layer, is asynchronous. What does that mean? It means that while, imagine you're in Zurich and it stores it in Zurich, so it's keeping you waiting until it replicates multiple times in the same location, but then it confirms, and the replication all the way to Frankfurt as an extra security doesn't keep you waiting. This is done later in the background, right? So you're already doing something else at that moment, but still it's going to also replicate a few more times to other locations, just for to be safe, right? To have more copies. There are several reasons, in fact, for replication across different locations. One of them is the latency. Imagine that you're hosting in your system the static pages of a website, and you have customers all over the planet. Well, if you are in Zurich and the pages are stored in New York, when you access the web page, there will be a slight delay. First, because of the speed of light. Even the light traveling from Zurich to New York and back for your request will take some time. But second, the internet doesn't have the speed of light. Right? There was work earlier by Professor Ankit Singla who discussed this. The cables are not in a straight line between Zurich and New York. In fact, the internet protocol might even do a few rounds all over the planet before it arrives there. So there is some latency. For the customers, that's not really good, because if all your customers have this feeling that they connect to the page, but it always takes a while in order for the page to load, that's not great. So what you do is that you replicate at a few places across the planet. If you have a copy in Zurich and a customer in Zurich connect, it will be almost instant, because that's just a round trip to the data center in the north of Zurich, right? The same goes, for example, somebody who is, I don't know, in Delhi, then you also have a copy of the data in Delhi, and then it's also instant, right? So this is very good for the customer experience. Second, natural catastrophes. Imagine that a data center burns down. It happens a few years ago in the east of France. There is a data center that burned down. They didn't make any backups. That was a catastrophe for all the businesses that had their data in there. You replicate to avoid that kind of things, for that kind of things to happen, right? So it's these two reasons. You optimize latency and you are resilient to natural catastrophes. All right, so this is what I wanted to tell you about Azure. I have no idea if S3 does it the same, but there is kind of the suspicion that it kind of does, that it's a bit similar. But if you use S3, in fact, you can still organize your data to be in a specific region, right? East of the United States, west of the United States, Frankfurt, and so on and so on. West Europe, Eastern Europe. All right, any questions so far? on cloud storage? All right. Then let me tell you a few words on something we are not covering in that lecture, but I just want you to know that it exists. This is something that I dive more into the master's lecture, is that there is another use case with a similar model with this idea that you have plenty of objects that are identified with IDs in a flat way, as I told you last time. And some people thought this would make sense to have a system like that that is in fact a database. So then you might think, okay, why don't we just do this, what I showed you right here, like this? We upload the data to S3 and there you go, you have your database, right? But that doesn't quite work for a database system that you want to be interactive or fast, because if you want to write to the system, you need, typically the latency is 1 to 9 milliseconds. It's in the single digits of the milliseconds. S3 has a higher latency than that. It's more like a few hundred milliseconds. If you want an interactive database system, that's just not fast enough. So you cannot directly use S3 as what we call a key value store. And so people invented key value stores. The difference with between S3 and a key value store is that a key value store doesn't have 5 terabyte objects. In a key value store, you're looking at objects that have a few hundred kilobytes. It's much, much, much smaller. And these key value stores are extremely efficient at writing and reading data. In fact, if you use social media like Twitter or LinkedIn, if you put posts or comments on LinkedIn and you edit and so on, this is typically stored in something that looks a bit like a key value store, right? Okay. Or I think the paramount use case would be when you shop online and you store the items you want to purchase in some carts, shopping carts, and typically that can go into a key value store. All right, but I just want you to know that they exist. There are key value stores, and key value stores are not the same thing as cloud storage services. The main difference being that key value stores have much smaller objects, and cloud storage services can have objects in the gigabyte and terabyte range, and they are a bit slower too. Okay? And a few last words. This is then because I mentioned Amazon and Azure. There's also Google. So these are the big three, and there are a few others. The mindset is a bit different. In Amazon, what you notice is that there are probably hundreds of different services that you can use. And they are on the shelf, and you can help yourself and use the services you want, right? And it's like assembling a puzzle. The Azure mindset is a bit different. You might have a bit less services, but these services can do more things. For example, one of them is Cosmos DB, that is a database that can do trees, tables, graphs, key values, and so on. So this is kind of good, I mean, for competition, that you have different flavors. But in spite of these differences, they all offer virtual machines, cloud storage services, domain registration, and so on and so on. So on the high level, they offer similar kind of things. All right, so what did we learn? We learned to simplify the model, flat key value model for object storage. We learned to buy cheap hardware, plenty of cheap hardware, instead of trying to have very expensive machines with a lot of CPU and memory. So plenty of hardware, thousands of computers in the same room. We removed also the schemas in the sense that key value doesn't have any hierarchy anymore, and like a local file system on your machine. But I don't want to get too much in that. I say a few more words on that in the master's edition of the lecture. All right. I have no idea why I had that twice, probably a copy-paste thing, but anyway. Any questions to conclude cloud storage services? All right, so that is our first service that we can use to put data in there, and then we'll continue to build on top of this. So now I'll move on to the next part then, distributed file systems. We are still going to store things. I'll be back in a few seconds. Yes, is there a question in the chat? Oh, yes, about the key value store. Yes, did we put it in the model? I might not have put it. I said it last week, but I might not have put it. The key value store, you can read it, of course. If you're curious, it's always good, but it's not part of the big data for engineers material. the key value stores, DynamoDB specifically. I said it last week, but we'll also add it on the Moodle to make it clear. But of course, if you want to read, if you're bored or if you think that this is going too slow and you want to learn more things, then you can go ahead and read it. It's just that we won't cover it in the exam. Anything else? Okay, then I'm going to stop here.